Our lesson today is on vector applications. Example 1. A commercial jet is flying from DFW to Cancun, Mexico at 516 miles per hour at a bearing 10 degrees east of south. The wind at the same altitude of the plane is blowing on a bearing of 20 degrees south of west at 42 miles per hour. So if we just think of this as a story problem in of itself, we know that the wind is going to have some sort of effect on the jet, right? We wonder, is the jet going to speed up in its mile per hour? Is the wind helping it, or will it slow it down? Would the jet be able to hold that bearing of 10 degrees east? Or, will the angle open up or close up a little bit? This is what we're going to discover as we work through this problem. So let's take apart this sentence, these two sentences, and focus on one vector at a time. So right now we're going to focus on the commercial jet, and there are certain characteristics that were provided for us. They gave us how fast the jet was flying, 516 miles per hour, and they gave us our bearing. The bearing is 10 degrees east of south. So you may not know how to read the bearing just yet, but I am going to show you how to approach that. So we're going to take that pink information and we are going to draw it out here to give us a sketch using vectors to help us understand the problem situation. Okay, notice that it does not need to be a scale. We're going to make one be a wind vector and the other one's going to be a plane or jet vector, however you want to call it. So the jet vector says that it's traveling at 516 miles per hour. I want you to make a note that this here actually is what our resultant is. That's the resultant, okay, which is basically our magnitude, okay? The length of the resultant is called the magnitude. Now the bearing, we're always going to do this in a rotational fashion. Make sure it's a circular fashion, as a matter of fact. So we'll rotate left, right, upwards, downwards, depending on which one of these pieces we're standing on. And the bearing also helps us find our direction. Okay, we need to know the direction of our position vectors. Direction as in our angles, okay? So, let us get to drawing. So I know the length of my vector that I'm going to draw is going to be 516 miles per hour. But what you want to do is focus on the bearing first, okay? Now the bearing says that it is 10 degrees east of the south. So my reference standing point is going to be the word that comes after the word of. It's telling me to go 10 degrees east from the south, basically. So here's my south piece, and I'm going to place my pencil anywhere here, it doesn't matter. But I need to go 10 degrees east. East is located over here. So if I'm going east, I'm going to rotate in a circular fashion from south to the right because it's east. Now 10 degrees is rather small, so you'll notice that when I drew this, let me zoom in here a second, that I am zooming in because that angle is so hard to see because it's pretty narrow. So from 0, 0, the origin, I'm going to draw a rather long vector because I'm going to make it a point that that is 516 miles per hour long, okay? So I'm going to label it saying that this is my jet vector, and the length of that magnitude is 516 miles per hour, and right here I'm going to say that that is 10 degrees, okay? It's kind of hard to see. To have a sharpened pencil as much as you can. Okay, now we're done with the jet. Now what I want you to do is pause the video and I want you to do the wind vector. Okay, so hopefully you did pause. The wind vector now, let's highlight that in yellow. The wind vector, they gave us 20 degrees, here, let me do it from bearing, let me do it this way, 20 degrees south of the west and 42 miles per hour. Now you can't see anything I just finished highlighting, so let me zoom out here for a second. Okay, so I just highlighted this in yellow. So bearing of 20 degrees south of west at 42 miles per hour. So let's go back to drawing this. We know that we need to stand at the west, okay, because it comes after the word of, okay. That helps us remember. So our west is right here, so I'm going to place my pencil wherever, and I need to go from the west, I need to go south. So south is downwards rotation. So 20 degrees, I need to rotate south. So it's going to be a little bit wider than that 10-degree angle. And so because it is 42 miles per hour, I'm obviously not going to draw this vector as long. Okay. So this vector represents the wind. So I'm going to say the wind, and it's traveling at 42 miles per hour. So in this picture that I'm providing, note that I'm just providing everything that was highlighted. Okay. Now here's the thing though. When you are finding your position vector, the angle or the direction of your position vector must always be measured from standard position. Okay, standard position is the positive x-axis starting from 0 degrees. So any angle measured as far as position angle, you need to always start from the standard position and rotate and stop wherever that vector is. Okay, so no, our angles are not going to be 10 degrees and 20 degrees. We're going to use those to find the direction angles. Okay, so over here, let's go find our jet direction. And then we're also going to find our wind direction. So here we go. I want you to notice what I'm going to do with the jet. Okay, so the jet vector is right here. So I need to start reading my angle from here, and I'm going to rotate a certain number of degrees. Okay, so I'm going to give you a little visual. Okay, so let me position this. So I am going to start way out over here. Okay, so I'm here at standard position, and I'm going to rotate in a circular manner. I've covered 90 degrees. I've covered another 90 degrees. I've covered another 90 degrees. And I need to keep going until I stop right at the jet. Notice I just stopped right there. So I just rotated. I'm going to remove this. Okay. That is going to be the direction for theta. So how many degrees did I travel? 90 plus another 90 plus a 90 plus this bit, which I know is 10. So 3/4 of a circle is 270 degrees plus the 10 degrees gives me 280 degrees for my jet. Okay, that's the jet direction. So I want you to pause the video and go find the wind direction. The wind direction will be found in a similar fashion as well. Let's see if I pick another, let's start it from about, let's try about right here. Okay, so I'm going to start right here. And again, I'm going to rotate until I hit the 20 degree, not the 20 degree, the vector with the wind. And I stop, hits there at the wind. I'm going to remove this. So how much did I rotate for this angle? Well, notice I again covered two 90s. Half a semicircle is a 180 degrees plus another extra 20. So 180 degrees plus the 20 degrees gives me 200. So these are our angles. These are what we will use, okay? So let me push forward up here. So notice that what was given to us in our problem is the length of the hypotenuse, okay, the resultant, and our angle. Whereas in our previous homeworks, what was always given to us were the x and y coordinates of our vector. This was not given to us here. So, for example, see this vector right here? If I started here, how far right and how far down did I have to go to get to my terminal point here? I don't know what this distance x is. I don't know what this distance y is. Same thing for here. If I start here and I need to arrive here, I do not know how much x to the left that I had to go or how much down I had to go. This is what we're going to do right here. That's what we're looking for. So let's go do that. So again, I give you guys a lot of detail in my writing out of work, but you don't have to write everything that you are seeing here, okay? So this is, write the velocity of the plane and the wind in component form, okay? So this is velocity of jet in component form. And then I'm going to do the velocity of the wind in component form. So what are we going to do here? Well, we are not able to use the formula that we've used before of x2 minus x1 and y2 minus y1. We don't have those x and y coordinates. As a matter of fact, that's what we're looking for, okay? So what you're going to do is you're going to use the following formula. If you take a trip back to right triangle trigonometry, and I don't have time to draw the triangle to show you guys why this works, but if you recall from right triangle trigonometry, if I'm looking for an x component, that usually is attributed to cosine values. So if I take my resultant for the jet, which is 516 miles per hour, what I'm going to do is I'm going to multiply it by the x and y component vectors, which will be found by finding the cosine of the angle of the jet, which we found up here to be 280 degrees, comma, and then I'm going to do the same thing but for the y value for 280 degrees. So this here, by multiplying this times this and this times this is scalar multiplication, you are going to get two values here that are going to give me the distance from here to here, which is going to be represented by this, and then the distance from here to here is going to be represented by the combination of multiplication of these two. So let's type this out. I'm going to type them both out at one time. So 516 times cosine of 280 is that. 516 times sine of 280 is going to be that. So this is my x distance and my y distance. Look how this makes sense, okay? My x distance had to go 89.6 to the right. So if I go 89.6 to the right, let's pretend that was 89. Then I had to go negative 508, negative 508. I do arrive to the terminal point of my jet. So those numbers make sense. So we're going to round those into two decimal places. So 89.60, comma, and negative 508.16. So that's the jet. I need you now to go find the x and y component of the wind. So pause your video right now and then come back to see if your answer is correct. Okay, so check your answer here. So notice we still use cosine for our x component, sine for a y component, but now we apply the angle for our wind and the magnitude for our wind. So you are using that magnitude and that angle. Again, just distribute, get those answers. Now, why did we do all that? Because the whole intent was to be able to combine both those vectors into one, because we want to know what is the effect the wind is having on the jet. So we are going to combine both of these vectors. We're going to add them so that we have one vector, okay? And you guys know how to add. This vector was given to us for Vj. This vector was given us for the wind vector. So if I added this plus this, I know I needed to add my x components together. So the 89.60 plus the x component of the wind, negative 39.47. For my y, I'm going to combine the y of the jet, negative 508.16, and I'm going to add it with the y of the wind, negative 14.36. Think of it as adding like terms, okay? So once you put that into your calculator, you'll end up with the answer 50.13, comma, negative 522.52. Okay? So what does that mean? So what they did was they took the combination of these two vectors to kind of give us an idea of what's happening now to the jet. Okay? So it seems like, okay, the location of the jet now, instead of it being, let me shift up here again, instead of it being located right here, whatever that point is, okay, it is going to be located in this fashion. And when we do the sketch, it's going to be kind of hard to understand the difference until we see the numbers. So I'm going to go to the right 50.13. So I'm going to assume that's 50.13, okay? So 50.13 miles per hour is the x component form. And then the y component form is telling us to go down negative 522, which is pretty much very long compared to that, 4 times longer, no, 100 times longer. And so we are just going to, did I say 100? 10 times longer. Goodness gracious. We're going to go down negative 522. So let's pretend that's about 10 times. Okay, and I'm going to label this side negative 522.52. So based on the vectors, this is the location of the plane now. So I'm going to draw the new resultant right here. Okay. And what we need to do is find this resultant. Okay, which, guess what? That is our actual speed. Okay, so look, don't you notice that this is a right triangle? And because it's a right triangle, that means we are looking, you can't see what I wrote, sorry again. You are actually looking for the hypotenuse. So if I'm finding this resultant, I'm actually looking for the speed, and that's the new speed of what the jet is. Remember, the jet was upstairs was flying at 516 miles per hour, but it's being affected by the wind somehow. So we're about to figure out how did the wind increase its speed or decrease it. So we need to find that distance right there. So how do we find the actual speed of the jet? Well, we're going to calculate the magnitude. Magnitude says, let's write the symbolism, the magnitude of the combination of the vectors that we just finished doing, okay, is going to be, finding the magnitude of that is telling us to do the sum of squares, and then you square root it, because, or it's a plus. When it's a negative, please put it in parentheses. Don't forget that, okay? So a squared plus b squared equals c squared, which is our hypotenuse squared, but in order to find hypotenuse, we had to square root it. So when you do that math there, you're going to end up with 524.92 miles per hour. So I'm going to write that number here, 524.92. So what do you notice? We started out at 516 miles per hour. The jet was flying at that miles per hour at the given, that was the given information. But with the wind, the effect the wind is having on it, it's causing it to actually fly a little bit faster than 516 miles per hour. That's actual speed of the jet. Once you combine the wind and the vector, it has an effect on it. Does it affect the angle? Well, let's find out, okay? So finding the angle is not any different to what we've been doing. Theta of our reference angle, we always find the reference angle by taking the tangent inverse of y over x. Well, the y value is that, and the x value is that. I'm going to label this here, so remind you. So y over x is negative 522.52 over my x value, 50.13. And once you do the tan inverse of that, second tan inverse of negative 552 over 50.13, we're going to get negative 84.52. So we want to round to the hundredth place. So negative 84.52 degrees. But that is our reference angle. That's not our direction angle, because remember, once again, our direction angle has to come from standard position and rotate, okay? This angle is definitely not that distance, okay? This angle was this distance right here. Starting from here, negative, rotating to the left. So what do? Well, quadrant location is important. We are located where? We are located currently in quadrant 4. This is quadrant 4. Okay. Because it's located in quadrant 4, we know that this point where our resultant ends, this terminal point, had to go positive and have negative values, okay? So that's why we know positive, negative values has quadrant 4 units. Oh, not units, signs, sorry. So notice it's a positive, negative vector location, okay? When it's in quadrant 4, the direction angle says to take the reference angle and add 360 degrees to it. Therefore, our direction angle will end up being, for this problem, 275.48 degrees. And if you truly look at this picture, you can see clearly that that is the case. Let's do this rotation here. So I'm going to start right here at standard position, and I'm going to rotate all the way till I get to my resultant stop, and it makes sense. 90 plus another 90 plus another 90 is definitely higher than 270. That little piece was about 5 degrees. Okay, and so that's our direction angle for the jet. So originally, if you look at it, 280 degrees, it deviated slightly by 5 degrees to 275. The original miles per hour of the jet was 516. The wind caused it to increase a little bit more to 524. So here's your challenge now. I want you to pause, and I want you to set up your vectors and then turn on your camera once you have also found your direction angles. Okay? Not turn on your camera. I'm thinking of Zoom. Unpause your video so that we can see if what you did is correct. So again, let me clarify. Sketch your vectors, find your direction angles. So pause right now. Okay, so let's talk about what you did. Let's start off first with the duck. The duck was 35 west of north, so of north, we start on the north, and going west means going left, so we went 35 degrees. So here was your duck vector. The wind, we needed to start from the south and go east. So here's my south. Going east means go to the right, so this was my vector right here. So let me zoom in here just a little bit to help you see more clearly. Okay, and so notice the labeling that has occurred. Now what I need to make sure is finding the direction angle for the duck and the direction angle for the wind. So notice that from here to here, I did go through 90 degrees plus another 35. And to get to the wind, I had to start again in standard position. I went through 1, 2, 3 quadrants, so that means 270 plus a little bit more. So if you look over here, this is what your direction angles should have ended up being. So we're going to use those direction angles to jump right into our vector components. Again, you are not going to use the formula x2 minus x1 and y2 minus y1 because in this problem we were given the resultant and the direction. So the formula is going to change. You're going to use your trig to find those x and y vector component forms. Okay, so again, the vector component for the duck, write down the magnitude. Cosine is x, sine is y. Don't forget that. This is always your x. This is always going to be your y. Distribute, and you're going to get those two answers. Let's do the wind. Take that magnitude. There's the magnitude, and now multiply it against the angle that you achieved to get to that vector. It took me the entire rotation of 295 degrees, so I'm going to use that. Distribute, write it down. But remember, the reason we got those vector components was to combine our vectors. We wanted to take these two and put them together so that we can see what kind of effect the wind is having on the duck. So let's combine the two vectors. So pause here if you need to do this piece now, and then come back. Okay, so welcome back. Here we go. So hopefully you remembered to add these by just adding the x's together, adding the y's together to create a brand new component form. Okay, so negative 25 plus 3, and negative 36 plus the negative 7. And right here, I wanted to point out that if you notice, I haven't drawn the picture out, but I can already tell where my quadrant's going to be based on the signs. This tells me to go left and then go up. So if you are looking at an x and y axis, if I go left for negative and up, notice that I'm in the second quadrant. So I don't necessarily have to draw anything to know which quadrant I am in. Okay, so moving on, we needed to graph the new vector to find the magnitude and then apply the Pythagorean theorem to find the length of that resultant of your new vector. So pause right here and let's see how you do that one. Okay, so first you should have sketched. So we are sketching the vector negative 22. Let me back up here a little bit here. We are sketching the vector negative 22.43, comma 2961. So that means here at 0, 0, I went to the left negative 22.43, and then I went up 2961. Okay, so this here is what I'm looking for. That's the length I'm looking for. And to find this, which is my hypotenuse, I needed to apply the magnitude formula, which is applying Pythagorean theorem, which when you did all the calculations comes out to be 37.15 miles per hour. So that's the length of this hypotenuse. Okay. Then what did we do? We needed to figure out this angle of direction. Okay, I'm looking for that angle. I can tell it's going to be above 90 degrees, but let's do the math, right? We know that we can take the tan inverse of the y over the x, which in this case will be, let me do it this way, the tan inverse of your y coordinate over your x coordinate. Okay, so there's my y over my x, and I get a negative 5286, but we already established that we are sitting in the second quadrant. Second quadrant requires us to take our reference angle and add 180 to it. So once we do that, we end up with our direction angle for the position vector of our combined vectors from above. So if you notice now, the 127 degrees is what the duck is flying at, whereas before it was flying at, what was it? 125 degrees originally. So look back at your paper. And then originally the duck was flying at, what was the speed? I can't find it, 45 miles per hour. But its speed is decreased tremendously because of the wind. He's now, or it's flying at 37 miles per hour approximately. So as you can see, the wind is definitely having an effect on the duck, and we can see what's happening based here. This is the final situation, looking at it pictorially. So hopefully this has helped you in understanding how to use vectors in real life world situations.